This problem states calculate the state of stress at location A, which is along the most positive y line or most y positive line on the surface of the loaded cylinder. T-app is in the positive x direction and M-app is in the positive z direction. If sigma y equals 100 megapascals, do we expect failure from the criterion of maximum shear stress, or Tresca criterion? So this is another problem that goes back to session 16 when we were discussing combined loading and being able to determine the state of stress when you have multiple external loads being applied. And you can go back and take a look at the analysis that we did there. I won't go into complete depth here, but I will go ahead and kind of briefly describe what's happening here. And it's a good idea to be able to essentially draw out the contributions from the individual loads. So there are four loads here, okay? And those are the PX, PZ, MAP, and TAP. Okay, so what's maybe a good idea is to draw four circles or four cross sections, generally speaking, with this point A, and and then think about what the contribution from the individual different loads might be on the state of stress. So let's go ahead and we'll do that. We'll first draw out four circles with location A on them. And this is one circle per load, like this. And, oh, they're getting progressively bigger. There, I made that one a little bit smaller. Okay, and so this first one we'll say is going to be contribution from px. Well, what is going on with px? Px is this axial load, and it's in the x direction, and so there is going to be some state of stress there. And it's just going to be essentially pulling in the x direction. So before I guess I kind of just already know from experience, hopefully not sad experience, but some experience, that the sigma x here is going to be the px divided by the cross-sectional area. And maybe I should just, instead of a and a, that's confusing. So we'll just go ahead and write it out as pi c squared. What does that look like here? Well, it's a little bit peculiar, but essentially what we're saying is here there's going to be a state of stress, right, coming right out at us, out of the board, right? So that if I were to try to draw a coordinate system, I could say, oh, I got x coming out and y going up and z going this direction. Because once again, we have x cross y, and that's going to be z, like that. Is px doing anything else to the system? No. It's not contributing shear stress. It's not contributing a bending moment. So that's all we have from px. So now let's look at the contribution from pz. Well, here what we see is that pz is going to the positive z direction, and it can create a bending moment that would be about y, but A is on the neutral axis, at least for that bending moment. That would be applied about the y-axis. So there's not going to be any bending stress because of PZ. PZ, though, you can think of it as acting across the entire surface. Okay, so if I think about it, as well, yeah, it's purple there, so that's fine. I can think of it as something like this, PZ. And so in that case, the opportunity for it to apply a transverse shear stress, if we think of this as a beam, is definitely there. And so it can, and if we think of the neutral axis as being in the vertical direction, right? We know that along that neutral axis, we're going to have the maximum transverse shear stress. So if you think about these little elements at all these little spots, we think, oh, there's a shear stress that's being applied across these elements, or on the faces of them. Okay, so like that essentially, and then we start to ask ourselves, well, that what direction would that be? And you can think of it as kind of similar to what we've discussed with let's say an element looking downward. Okay, and so in this case, what we've got is the shear stress acting in the positive z direction, and it's on the x face. So we can say that the contribution from PZ would be a tau. It's acting on the x face, xz, okay, which is going to be what? Well, we've got transverse shear stress. This is a cylindrical cross section. It's maximum transverse shear stress. So we can say it's 4/3 times tau average, which is going to be 4/3. So 4 times the PZ over 3 times pi, and the radius is c squared because that's the area. So does PZ do anything else? No, that's it. It's not causing twisting. It's like we discussed. It does cause a bending moment, but that bending moment doesn't lead to any normal stresses. And we've got a transverse shear stress. Okay, so that's that. Let's go down to contribution from MAP. Well, in this case, MAP is about the positive z direction. So this is about positive z axis. Okay. And we can kind of get a sense that, oh, if I were to take this beam and apply that moment about z, that's going to put the top into an amount of compression, right? And the bottom of this rod, or this beam really, and since we're talking about bending, that would be under tension. And what is the way to figure out what that normal stress from bending is? Okay, well we can calculate that out, right? We can say that the and which direction is it going to be? Well, it's going to be sigma x, so we'll say that sigma x is going to be compressive, so we're going to have a negative m app, and the flexure formula, right, is going to be negative my over I. And in this case, the way things are looking, it's got a positive m app and a positive y, but a negative sign in front of it. So it's going to be negative m app c over the I, and I for um, a circular cross section, right? The second moment of area for a circular cross section is going to be pi over 4 c to the fourth. Okay? And so that is what we're going to have. Okay. Now, is it doing anything else? Well, you could argue maybe since it's bending, you could say could there be a transverse shear stress? Well, in fact, no, not from MMAP, because MMAP, the way this is being applied, it means that it's MMAP across the entire span of that beam. And remember that V, the internal shear force along a beam, is equal to, right, just remember that V is equal to dm dx. Well, MMAP is constant, so that means that V is going to be equal to 0. Okay? And so there's not going to be a transverse shear stress component from this bending. So we're done there. Now let's go down and finally look at the contribution from TAP. Okay, and so TAP, we've actually done this problem in the last one that we looked at, question 2 from session 22. We know that this is going to be contributing a shear stress, and it's in the same direction that I drew right there for that arrow. And so that means that it's also going to be a tau xz, and that's the TC and J formula. Okay, so that one is going to be a tau xz, which is equal to Tap times C over J, and J is pi over 2 C to the fourth. Okay, so we're going to end up with a 2 Tap over pi C cubed, and this one that we had, this sigma x, I guess we can simplify a little bit, and we can say that it's minus 4. I'm just going back and trying to be somewhat clean. Pi c cubed. Okay, like that. So they have the same units. It's a moment or a torque over pi c cubed. And anyway, it has to come out to be a stress. So when we combine all these things together, what are we going to see? We're going to see that the state of stress, we have sigma x up here, sigma x here, we have tau xz here and tau xz here. We're going to have, if I use a different color, sigma x equal to the px over pi c squared. And then what was the other one down here? Minus 4 map over pi c cubed. And we're going to have our tau xz equal to, well, there's a positive contribution here, and there's a positive contribution here. So that's going to be 4/3, that's up here, that's this one up here, times pz over pi c squared plus the 2 Tap over pi c cubed. Right? So we've redone this problem. Now, the question is, do we expect failure from the criterion of maximum shear stress, Tresca? And they give us a number, but we don't have any numbers here. So let's just talk about what we're going to be looking at and calculating. This is a situation where very likely you've got two positive. I mean, it depends on, is MMAP really large or is PX really large? What was it, to see whether or not it's positive or negative. If they're both, I can just do a couple things. If sigma x and tau xz are greater than 0, okay, and we can do if sigma x is less than 0 and tau xz is greater than 0, okay, and assuming that the p's, all these loads are positive, and they're acting in the direction that they're given here, right? These are kind of our two scenarios. So we can go ahead and we can draw out our more circles. for these cases. And so if we do that, we can say, all right, they're both positive. Okay, and I'm going to say that the the rest of the rest of the stresses are zeros. So I guess we could say, make a little note here that that sigma y equals sigma z equals 0, and that tau xy equals tau, what do I got? Yz is equal to 0. Okay, so the other states of stress are 0. So when we look at this situation, we have a sigma x and then we have a tau xz. So we're going to be working in the xz plane essentially. And whoops, I completely missed that. Okay, that's tau. This is sigma. We would say, all right, what is the sigma average? Well, the sigma average for this situation, right? Uh, Sigma z is equal to 0, right? So then we'd be saying that the sigma average is just going to be equal to the sigma x over 2. And sigma x is going to be out here, right? So this is going to be the line for sigma x, like that. Okay, and what is tau xz? Well, tau xz is going to be down here somewhere, right? So we can say, all right, we got, maybe I don't want to, let's do that. We'll just say that's our point of operation, okay? And the radius, therefore, is going to be something like this, r. And what we're going to have is a circle, and this is really bad, but it's going to go, okay? And I'm just, because I didn't want to knock out my other things, right? It's got to go on the other side of uh, the vertical axis here, the tau axis. So does that tell us? Well, I mean, it depends on what these values are going to be, right? But what do we know that the maximum shear stress is going to be for this system, right? Because that's what we're looking at. We know that that we had this, it was over here, right? So this point right here, that was a 0 comma minus tau xz, all right? And given that the rest of the states of stress are 0, we're going to be here, no less. So our sigma 1, all right, this could be your sigma 1 here, this could be your sigma 2 here, and this could be our sigma 3 here. And the Mohr circles are going to be something like what we're showing. And again, these are very distorted. They're more like Mohr's ovals, okay? And so the absolute maximum shear stress is going to be down here, all right? It's the radius. Now, what's the radius? Well, the radius, you're going to have to, you can calculate it out. In this case, the radius has to be calculated, because I don't know what sigma 1 is, but if I had to do this, right, what I had to say is, okay, the radius is going to be the sigma x, okay, minus the sigma x over 2, right, that's the sigma average, squared, plus the tau x y squared. Okay, so that's the radius. And so what it comes down to is that's the tau absolute max, which is equal to the radius. And if this tau absolute max is less than the maximum shear stress, all right, so if tau absolute max is less than the uh, sometimes we say SSY, so that's the shear yield strength. Okay, then we don't have failure. Then no failure. Okay. Now, did they give us SSY? No, they did not give us SSY. They gave us sigma y. All right. So now we had to think, oh, well, what's the equivalent SSY? And this is where we talked about it in class. The most famous method of loading and material testing is the tensile test, right? And this is loaded to the yield strength, right? And they did give us the yield strength, right? It's loaded to the yield strength because that's when we're going to have yielding. That's when we say we have failure. Okay, and if we're using like a linear elastic, perfectly plastic model, that's where it flatlines, right? If you look at the stress strain curve, right? You remember these from a long time ago? It would look something like that. And then, so the maximum that you can have is SY. But I need to know SSY. I need to know the shear strength, the shear yield strength, all right? So how do I do that? Well, that's where you draw another Morse circle. And we say, look, we are at SY, and the other stresses are zeros, okay? The sigma 2, the sigma 3, so this is like the sigma 1, okay? And so that's a Morse circle that just looks like this, okay? And so the maximum, okay, the SSY, because I should be careful here. Let's just say that this is SY, okay? And now this is SSY, like this. That is going to be the radius here. So that means that SSY, right, what's the radius? It's sigma 1 over 2. Sigma 1 is equal to SY. So that means that SSY is just going to be SY over 2. So what we're saying is that this SSY is equal to SY over 2. So as long as the absolute maximum shear stress for our system is less than SSY, or the yield strength divided by 2, we don't have failure. Okay, now, the other scenario, it comes out to be very similar in that if we have the description of Morse circle, okay, so we're going back to this. If sigma x is less than 0 and tau xz is greater than 0, all right, then what we're going to have sigma tau, okay, we're going to have something where the x, okay, so this would be our sigma x line, right, because that's negative. And we have that the average, right, is going to be halfway. And so when we plot it out, we're going to have this point here, which would be sigma x, comma, tau x, y, okay? And this is going to give us a radius. And when we go around, we have to go just past the origin, okay? Just like that. And that's what the Morse circle is going to be like, looking like there. And so once again, we're trying to figure out what is the absolute max shear stress because loaded. Because the other ones, right, this is sigma 1, and these are sigma 2, sigma 3, and we're going to have little more circles inside that do something like that. Okay, I know, very, very crude. Very, very crude. And the tau absolute max is once again just the radius of that big circle, okay? And that is that you know, what is that? That can be the same exact formula right here. That's the, or sorry, that, maybe not that. The radius, right? R, we've already calculated that out. And you know, this is a square, so whether you know you got the negative sides, whatever it is, it's going to still end up being a positive number when you calculate this r. And so once again, the question is um, about whether or not this absolute max shear stress, this tau absolute max, is less than the SSY. Okay. Now that's using Morse circle. Let's talk about what this looks like on a sigma 1, sigma 2 plot. So let's talk about sigma 1. Okay. For a ductile material and using the Tresca criterion, the sigma 1, sigma 2 plot will look something like the following. Okay, well, whoops, I'm too used to drawing more circles in this class. So sigma 1, sigma 2. Here in the quadrant 3 and in the quadrant 1, we have these box-like shapes, and we just go out to sy, comma, sy, and minus sy, comma, sy. But then in the quadrant 2 and quadrant 4, the envelope is not this box shape, but it's not this box shape, it's actually a line. Okay, and so what we're trying to do is figure out, are we in the box or are we out of the box? Okay, and this can be a little bit tricky because you've got to be thinking, okay, what is my my maximum uh, what are my sigma 1, my sigma 2, right? This not showing the the, the shear stress directly. So in this particular case, right, what we're going to be looking at is essentially, okay, sigma 2 and sigma 3. Sorry, I did this wrong. Sigma 3 is at the middle. Okay, sigma 2 is out here. Okay, that's this little point out here. So I can write out that sigma 1, and I had to calculate out what that radius is, right? But sigma 1 is going to be r plus the, and I'm kind of taking some liberties here because sigma 1 is really negative, but I'm looking at the magnitude of it. So I could do that here. Maybe I'll do it, let's look at it, let's just draw it over here just so we're a little more clear. Sigma 1 is really the sigma average, so it's going to be the sigma x over 2 plus r, and sigma 2 is equal to the sigma x over 2 minus r. Okay, that's what those values are. Okay, because we do know that the center of that circle is at sigma x over 2. So those are the two, the sigma 1 and the sigma 2. So we're, if we're over here in this area, if we're over here, it's going to be different. But let's just take this one, for example. When they're both positive, that means that sigma 1 will be positive, sigma 2 will be negative. Well, where does that happen? Sigma 1 being positive, okay, down here in quadrant 4, where sigma 2 is negative. So the question then you want to ask yourself is, am I in this part or am I in this part? Okay, and that can actually be a little bit tricky in terms of figuring out, okay, which side of the line am I on? And so what you can do is you can actually come up with the equation for this line. Okay, well, where are the points? The points are at 0 comma minus sy. That's this point right here, and this point is sy comma 0. And you're like, wait a second, the slope of this line is positive 1. All right, and I have a y-intercept at minus sigma sy, right? So now I can even write that the equation of this line So this line right here has the equation of sigma 2 is equal, because that's the y, or that's the vertical axis, is equal to the y-intercept, right? Or I could do the slope, whatever I want, but sigma 1, where there's nothing, right? The slope is 1. So I just have b, and this is, this is a form of mx plus b, right? So the m is 1, so sigma 2 equals sigma 1, and the y-intercept is equal to minus sy. So what do? I have to uh, essentially test the value for what I have for my stress and see if I'm above or below the line. And how do I do that? Right, so maybe, or am I above or below the line for a given sigma 1? Okay, so I can plug in, how do I figure out sigma 1? Sigma 1 is, so I take this equation, I have my sigma 1 from over here, is equal to sigma x over 2 plus r, and then I plug it in here, okay, and I'll get sigma 2 on, we can even call this like sigma 2 yield, all right, and if my sigma 2 that I calculated, this one right here, right, I had to compare sigma 2 to sigma 2 yield, so if sigma 2 is greater, okay, which means less negative here, all right, because it's got to be above, then sigma 2 yield, right, then no failure, okay, because I'll be in the envelope. This is the envelope. The envelope is all that, right? If I'm in the envelope, then I will not have failure. If I'm outside the envelope, then I will have failure. Okay, so that might have been a long video to kind of explain how to attack this problem, but I hope it's helpful. Yes, you can use the Moore circle to identify whether or not you're going to have failure due to Tresca criterion for absolute maximum shear stress, or for shear stress. But we can also use these sigma 1, sigma 2 plots kind of with more circle to figure out if we're going to have failure as well. And in a little bit, and soon, we'll be talking about how to also calculate what's called a safety factor. So if you were to increase the load, how much would you have to increase the load by? Or how much would you have to multiply that load in order to then induce failure? And that's how you calculate what your kind of margin, your budget, your buffer for safety might be. And that's the safety factor. All right. Thank you.